Okay, so here we are moving into chapter 13, chemical kinetics. Apologies that we can't be in person today, but we'll do our best with a virtual lecture. So chemical kinetics is an interesting topic. You'll get a lot of chance to update your math skills, and we'll see how that goes for those of you who may have been a little rustier in terms of logs and natural logs. So before now, we've looked at chemical reactions and we've just sort of said that they'll happen or they won't happen, and that's all about thermodynamics. So thermodynamics is about a reaction's energy requirements. So it tells us if the reaction is favorable and the product is formed with the release of heat, or if the reaction is unfavorable and in order to form product, heat has to be absorbed. So that's sort of a Chem 1 idea of things. Now that we're in Chem 2, let's get a little bit more about the details. So chemical kinetics, kinetics specifically deals with the rate of reaction. So it's about how fast a chemical reaction goes from reactants to products. So reaction rates, we'll talk about different rate of reactions and reaction orders and all that stuff. And also toward the end of this chapter, we'll talk about how the reaction happens. We can write them on paper. As you see, 2H2 gas plus O2 gas is in equilibrium with 2H2O gas. But that doesn't really necessarily describe the path. It probably doesn't happen all at once like that, even for something relatively simple like this reaction. So we'll talk about how reaction proceeds in a detailed way, and that's known as the mechanism. So that'll be at the end of this chapter. So if chemical kinetics discusses the speed, the rate of reaction, then we have to understand the factors that are going to affect these reaction rates in order to ultimately understand why the rate is what it is and why the mechanism explains a particular reaction process. So let's talk about rate. Of course, speed is our everyday word for it, but now that we're Chem 2 students, we're going to talk about rate of a chemical reaction, and that's known as the reaction rate, simply enough. It's about a quantity change over a given period of time. So if we think about an everyday example, the speed you drive your car is the rate in terms of distance that the car travels in miles here in this country, but kilometers in the rest of the world during a given period of time. Usually miles per 1 hour is the standard that your speedometer reports. So the rate your car travels has units of miles per hour. If we're looking in chemical terms, then now the rate of reaction is a measure of how fast our reaction makes products or uses up reactants, right? We tend to look at the decrease of reactants rather than the formation of products here in our beginning study of kinetics. So we're back to molarity for units. So the reaction rate measures how much concentration, molarity, moles per liter, of a reactant decreases in a given period of time. So for reactants, we get a negative sign because we're losing reactant as the reaction progresses. So the rate of a reaction would be equal to the negative change of concentration in molarity of a reactant over the change in time. If we were following the products instead, then it would be a positive because products should increase as a reaction goes forward. All right, just wait until we get to chemical equilibrium and then we'll throw that all on its head. But for now, we're looking either at the rate of disappearance of reactant or the rate of appearance of product. If we're going to follow reactant as we normally do, we need a negative sign before that change because the reactant is decreasing in molarity as the reaction proceeds. Now, if we haven't complicated things enough already, here's a time to complicate things further. So when we talk about chemical kinetics, we're talking about rate of reaction. Rate has different specific meanings, so let's be very clear about rate. So let's talk about a couple of different rates here on this slide. So we have instantaneous rate. So the instantaneous rate is the change in concentration at any one particular time. Those of you who have calculus, even though this is not a calc-based course, you might recognize that phrase of instantaneous rate and think about derivatives and all that good stuff. Well, for those of us without the calc background, we're looking at the slope at any one point of a curve. That's our instantaneous rate. And so it's determined by taking the slope of a line tangent to the curve at that particular point. It's also the first derivative of the function if you are a Calc 1 fan, or at least someone who's completed the course and remembers that much from it. Another rate that we'll talk about is the average rate. And so the average rate, rather than being at any given instant along that slope of the concentration time plot, the average rate is the change in measured concentrations in any particular time period. So we've got two different times, and we're going to average the rate across those two different times. And this is therefore a linear approximation of a curve. So we've taken 2 points along the curve and we've made our own tangent line that has a slope there that's running through both points. The larger the time interval, the more the average rate would deviate from the instantaneous rate, which, as we mentioned above, deals with just one particular point on that graph. Okay, so looking at these ideas graphically, we have a reaction H2 gas plus I2 gas reacts to form 2 HI gas. So in this particular case, if we want to consider the instantaneous rate at 50 seconds, well, it's tough to really just consider that without considering at least 2 points. So what we'll do is we'll draw a tangent line to that graph at 50 seconds. And we can do it for the HI product, or we can do it for the H2 reactant, or the I2 reactant for that matter. In this case, first, let's look at the H2. So using the concentration of H2, the instantaneous rate at 50 seconds is, well, if we recall that we're dealing with a reactant, therefore we need to negate it, so rate equals negative. And then if we look at that change in H2, if we're looking toward the bottom of the graph, so from that tangent line that we've drawn, we'll look at times really going from, say, 30 seconds to 70 seconds, and we've decreased our concentration by 0.28 molar in that range, and that's a 40-second interval that we're considering based on the tangent line we've drawn. So that's where that delta T of 40 seconds comes from. And if we do that calculation correctly, we end up with a rate of 0.0070 molar per second. If we go up top instead and look at the rate of appearance of HI, notice along that same interval where we draw the tangent line at 50 seconds, and then we consider from, say, 30 seconds to 70 seconds, that's the same delta T, that same 40 seconds as up above. This time we've increased our amount of HI by 0.56 molar. So the rate here equals and no minus sign, but we have done a half. Notice that half out in front? Well, that's because we make 2 moles of HI for every 1 mole of H2 and I2 that react. So that's why we had to take half of our concentration, because we are creating twice as much product as reactant that we're consuming. So 1/2 of that 0.56 molar difference over that 40-second interval gives us the same rate. Again, the instantaneous rate at 50 seconds should be the same for any reactant or product that's under consideration, and we do see that it's 0.0070 molar per second for the rate of appearance of HI, just like it was for the rate of disappearance of H2. All right, so now that we've looked a little bit at a specific example, let's think more broadly. Let's look at the general factors affecting rates. So if we want to think about what's going to speed up or slow down a reaction, let's think about the key features of a chemical reaction. So first and foremost, we have concentrations, and these are molar concentrations, right? We're done with our previous chapter where we talked about molality and mass percent and mole percent. We're back to our standard chemist unit of molarity here for concentration. So the more stuff we have, the more likely that these molecules are going to find each other and react. So concentration is obviously very important. Secondly, the physical state of the reactants in the products. We've dealt so far with gas phase reactants, and that's nice because as gases, they're not entangled with each other. If we think about a solid state, really only the surface atoms or molecules or ions are available for reaction. So being in the gas phase or being dissolved in solution, a liquid phase solution like we've been dealing with in the previous chapter, is a nice place to be. It allows for much better surface chemistry than if you're stuck in the bulk of a solid. Temperature, clearly, if you want to speed something up, you probably know this, a good way to speed things up is to heat them, right? So temperature tends to play a big role in affecting the rates of reactions. And then finally, catalysts can affect the rate of reactions. They shouldn't affect the overall position. We'll talk about that next chapter on equilibrium, but they do play a role in speeding up at least one step in a mechanism, if not an overall reaction. So those are some features to think about, some key factors affecting rates of reaction. Okay, so if we look at that phrase nature of reactants. So the nature of reactants means the physical state of the reactant or reactants. So let's take a look at some key ideas here. So small molecules tend to react faster than large molecules. And that has to do with the average kinetic energy, right? A small molecule at the same temperature is on average moving faster than a large molecule at the same temperature. We also have the idea of the sophistication. If it's a large molecule and only a small portion is reactive, then that's going to take a while for the reactant molecules to find that reactive portion. Then if we have a small molecule that's relatively available and ready to react, you're going to have a lot more success in getting those molecules to react. Gases tend to react faster than liquids, which react faster than solids. So that should make sense based on our discussion in the previous slide where we talked about the surface is where it's at. Gases are all surface. Liquids, again, if you have reactive species dissolved in a liquid, then they are also quite available to react. Solids, you have reactive surface, but the bulk is buried in the center of the solid, and it takes longer to react. Powdered solids are more reactive than blocks or clumps of solid material. Again, that deals with the concept we just mentioned. The greater the surface area for contact with other reactants, the quicker the reaction will be. It's all about the surface. A powder, it's still a solid, but at least it's a high surface area solid relative to the bulk. Certain types of chemicals are just plain more reactive than others. So if we think about the activity series of metals from last semester, we had a lab where we looked at the reactivity of metals, and certainly more active metals are going to react faster than less active metals. So if you think about aluminum, for instance, aluminum is quite a reactive metal compared with something like gold, which is a very noble, non-reactive metal. Finally, ions react faster than molecules. You don't need to break bonds like you do in the molecules. The ions are ready to react and find other ions and make, in most cases that we study, make some solids, right? Precipitation reactions of ions. So there you have it, a brief run through of the nature of reactants and how that affects chemical kinetics by affecting the ability to react. All right, looking further, let's talk about concentration of reactants. We already mentioned this before, but in general, the more concentrated the reactant or reactants, the faster the reaction occurs. So the reason for that is the more stuff you have in there, the more reactant particles there are, the greater the frequency of reactants colliding with each other, making contact, more chance for the contact to be successful when you have more particles present. Just statistically speaking, if there's more particles in the solution, then there's more of a chance they're going to touch one another and contact in a way that leads to a successful reaction. The concentration of reactants in the gas phase depends on the partial pressure of the gas, if you remember that from Chem 1. So if we have a higher partial pressure of a particular gas, then that reaction we'd expect to go faster than if we had a lower concentration or lower partial pressure of that gas. For solutions, the concentration depends on the solute to solution ratio, so the molarity, right? And we can deal with molarity of gases too. We just are reminded here that we could also deal in partial pressures for gases, whereas we're restricted to molarity for solutions, liquid phase solutions, I should say. Temperature has a big impact, as we already mentioned. Increasing the temperature will increase the rate of reaction. Here's our chemist rule of thumb. Again, it's not necessarily true exactly, but a good general rule is for each 10 degrees Celsius rise in temperature from any reactions, the speed of that reaction doubles. So that's, again, just a rule of thumb. We're going to do lots and lots of math later on to figure out exactly the impact of an increase in temperature, for instance. But for now, we'll just say that roughly speaking, for many reactions, 10 degrees C increase in temperature results in a doubling of the rate. The mathematical relationship between that temperature and the speed of a reaction is given in the Arrhenius equation, and we'll dissect this one later on, but for now, suffice it to say there's a frequency factor and an activation energy and an exponential factor that will all come into play, and that will have a role in determining the overall rate of a reaction at a given temperature. Now, the last of those features to discuss are catalysts, and catalysts are substances that affect the rate, the speed of a reaction without being consumed. They can participate in a given step, as long as they're regenerated in a later step. So they start and end in the same physical state, so therefore we say they do not get consumed in a reaction, but again, they may participate in a given step, and they may catalyze a particular step or steps of a reaction. So most catalysts are used to speed up a reaction. These are called positive catalysts. Catalysts can also be used to slow down a reaction, and they're known as negative catalysts. So catalysts don't necessarily always speed up, they just can always affect the speed. So most of the time we're looking at a speeding up, but sometimes, rarely, we do get negative catalysts. There's a couple of categories of catalysts. We have the homogeneous catalysts, which mean the catalyst and the reactants are present in the same phase. So for example, we have our biological systems where cellular reactions occur. Pretty well everything's dissolved in aqueous conditions there. You can also have heterogeneous catalysis. Catalyst and reactants are present in different phases. This is more likely the industrial style catalysis. So if you think about your catalytic converter in your automobile, very expensive piece because of the platinum that goes in there, that's an example of a solid catalyst that affects a gas. In particular, carbon monoxide gas is made less harmful. It's rendered into CO2 by the catalytic converter. The solid phase catalytic converter affects a gas phase reactant. Catalysts can affect a reaction rate by lowering its activation energy, in the case of positive catalysts anyway, and that's what lets the reaction occur more quickly. So by lowering the activation energy, you have more molecules that have the necessary energy to get the reaction going, and therefore, for reasons we talked about with concentration, the more molecules that are reactive, the faster the reaction will occur. So we've already mentioned a rate of reaction in terms of an instantaneous rate and an average rate. Well, now let's talk about the rate law in the reactant concentration. So for a given reaction where we have lowercase a, which would be our stoichiometric coefficient of capital A, which is our reactant, going to products, the rate of reaction is proportional to the concentration of reactant capital A. So the above reaction expressed as a rate law, which describes the rate of reaction, would be rate of reaction in molarity, concentration per unit time, equals some constant times that concentration of reactant A raised to a given power, an order as we call it in kinetics. So lowercase k is the rate constant, n is the reaction order for reactant A, and then the rate constant is actually independent of temperature is independent of concentration for that given reaction rate, but it does increase with temperature. So the lowercase k, the rate constant, is temperature dependent. It would change its value at a different temperature, so you have to be careful that you're using the correct k rate constant for the reaction conditions in terms of temperature. Again, n is the reaction order, and we'll talk more about that briefly. All right, all about reaction orders. Was that a brief enough pause for you? So for the chemical reaction, lowercase a, which is our stoichiometric coefficient of uppercase A reactant, plus lowercase b of uppercase B reactant, go to C, stoichiometric coefficient of capital C product. So the rate law here is rate equals K, that rate constant, times the concentration of A raised to its order, which we've generalized here as N, times concentration of B raised to its order, which we've generalized here as the lowercase m. So those exponents N and M are referred to as the reaction order, and reaction orders can be positive or negative whole number integer values. So -1, 0, +1, 2, or they can be fractional. Things get really interesting here in kinetics, so just be aware that it can get fairly complicated fairly quickly here. We'll try to keep it as simple as we can, but it's messy. Reaction orders must be experimentally determined. You can't just predict them from the reaction that you've written. The reaction rate orders cannot be obtained just from the balanced chemical reaction. Don't make that mistake. We will be using balance coefficients when we get to equilibrium, but for kinetics, we have to go with the experimentally determined rate order. The sum of all the reaction orders, the exponents there for all of the reactants, is called the order of reaction, the overall order of reaction. In the case of rate equals K, A to the second power, B to the third power would be fifth order overall. We've taken the 2, the exponent, the order of A, plus the 3, the order of B, and we've added them to get fifth order overall behavior from that reaction. All right, so let's take a look at some of the more common orders that we'll encounter here in Chem 2. So zero order, the rate of the reaction is independent of the reaction's concentration. So here we see a zero order plot where we have the concentration as the y-axis and time as the x-axis. Here we see the reaction's concentration decreasing, the reactant concentration rather decreasing linearly over time, so our slope is minus k. Our rate would therefore be k times a to the 0 power, or since a doesn't really matter, as long as there's some a it reacts, we have rate equals k, so the rate law equals this rate constant in a zero order reaction. Okay, instead, let's consider first order reactions. So first order reactions, the rate of reaction is directly proportional to the reactant's concentration. This makes a lot of sense. This is what people tend to be able to wrap their minds around. So the reactant's concentration slowly decreases over time, and the rate is changed by a given factor based on if you increase or decrease the concentration by that same factor. So first order kinetics tends to be what everyone wants to do all the time. Unfortunately, nature doesn't do it that way. We do have zero order, and we'll talk about second order in a moment, and we have those fractional orders and negative orders and lots of other things that will happen from time to time as well. But here, for first order, rate equals k, the rate constant, times the concentration of A to the first power, or simply rate equals k times concentration of reactant A. All right, the last order we'll talk about explicitly here in our course is second order. So in second order reactions, the rate of the reaction is proportional to the concentration, the reactant's concentration. So the reactant's concentration again decreases linearly over time. And here we see that slope equals k behavior. And notice now we've plotted 1 over a rather than plain old a like we did in the first case, or last case I didn't point it out, but it was actually the natural log of a in the previous example. So zero order, just plain old concentration versus time. First order, natural log of concentration versus time. And now second order, 1 over concentration versus time to get us our nice straight line slope. So rate for second order reactions, rate equals k times the concentration of that reactant raised to the second power. All right, so we mentioned that reaction rates have to be experimentally determined in order to find the order of a given reactant. So let's talk a little bit about how we derive reaction rate laws by inspection of experimental data. So one way we can do it is we can look at 2 sets of data, and we can compare the reactant concentrations to their corresponding reaction rates. So for instance, if doubling a reactant's concentration corresponds to A, no change in the reaction's rate, then the order is said to be zero order, right? We said for zero order reactions, it doesn't change the reaction rate to change the concentration. Another possibility would be doubling that reactant's concentration would double a reactant's overall reaction rate, and then therefore the order is said to be first order. So whatever we did to the reactant, we did the same thing to the rate. That's evidence of first order behavior. If, on the other hand, we doubled that reactant's concentration and we get a quadrupling of the reaction's rate, then that's second order behavior, right? 2 to the second power would be 4. So if we have second order behavior, we would expect whatever change we made to the reactant concentration, we'd expect that change to be squared in how it behaves in the new condition. So there we have it, a few ways of looking at data and figuring out what the reactant order is. All right, another thing to consider here when we're talking about figuring out overall orders and such, we have to consider the units of the rate constant, that lowercase k. Those get determined by the overall order of the reaction. So the quantity rate has units of concentration or amount of change per unit time. So for chemists, we tend to focus on molarity per second. So molar per second tends to be our units of rate. But you could also think about milligram per year for, I don't know, something like a nuclear reaction or something like that. But we tend to focus on the molar per second end of things. So let's look at an example. Let's look at that same example we talked about a few slides back. Rate equals rate constant k times a to the second power times b to the third power. So we mentioned that the overall rate there is fifth order. To determine the units of K, well, rate itself has to be in units of mole per liter second. So that's seconds in the denominator too, right? Or big M, s to the minus 1 is another way you'll commonly see it. And that's going to equal K times mole per liter, which is the concentration unit, to the 5th power, because we have 2 and 3 as the orders. So K units have to be such that both sides of the rate law will have the same overall unit. So in this example, the units of K, in order to keep that mole per liter per second rate, we're going to have something that gets rid of 4 molars, right? So m to the minus 4, s to the minus 1 would be the units of K here. All right, so that's how we're going to decrease things so that we end up with a rate expression on the left-hand side with units of molar per second, and on the right-hand side, K is going to adjust the molar to the 5th to be molar to the minus 4, s to the minus 1 to get overall units of molar per second on both sides of the equal sign. Let's take a look at an actual problem and see how this all relates to order. So using the experimental data given in the table, derive the rate law and determine the units of K for the following chemical reaction. So we have just one reactant gas. That's nice. That makes life actually much easier than usual, believe it or not. And it yields methane and carbon monoxide as products. So if we look at that starting reactant, we have 4 different experimental runs, and we've just taken 0.1, 0.2, 0.3, 0.4 as the initial concentrations, and we find that we get a rate of 0.020, 0.081, so on and so forth as we go down. So let's take a look and see what we can do to figure out the order of reactant in this example. Okay, so how do we solve this? Well, we take a look. The first 2 reaction runs are probably the easiest to compare. We take reaction 1, where it's 0.10 molar concentration of reactant and a rate of 0.020 molar per second. Compare that with reaction 2, where we're 0.20 molar reactant concentration and 0.081 molar per second rate. We've roughly doubled the reaction concentration, and we've roughly quadrupled the rate there. So if doubling their concentration results in the quadrupling of rate, we said before, that's an indication that the reactant is second order. And we can take a look now at the rate law, where rate equals K times CH3CHO to the 2nd power. The units of K in this example would be liters per mole per second, or a molar to the minus 1 per second. So that's how we would apply these concepts in an actual problem. Okay, sometimes things are a little more complicated, like this reaction here, where we actually have to consider 2 reactants. So if we look at the reaction, CH3Cl gas plus 3Cl2 gas yields CCl4 gas plus 3HCl gas. So if we look at the experimental runs, we can see that there's now another way to approach this, and if you haven't caught on just yet, give us a moment and we'll point it out. Okay, so here we see that we have in experiment runs 1 and 2, we haven't changed chlorine concentration, but we've doubled the CH3Cl concentration, and that's roughly doubled the rate. Likewise, if we're looking at reactions 2 and 3, we've kept the CH3Cl concentration constant, and we've roughly doubled the chlorine concentration. So that's what you're looking for. You're looking for the orders by looking at the reactants that have changed and the reactants that haven't changed when you're looking at these different experimental runs. So that's what's going to allow us to find the rate law and then ultimately solve for the unit and value of K in a case where we have multiple reactants like this problem. All right, so looking at runs 1 and 2, where we kept chlorine concentration constant, we can see that what we're left with is a factor of doubling reaction concentration for CH3Cl and a doubling of the rate. So if you want to do it rigorously, we can do logs and things like that, but by inspection, just by those approximate values, we can see that this reaction is first order with respect to CH3Cl. When we're considering chlorine, on the other hand, we have to look at reaction runs 2 and 3, and we see that it's not so neat and clean this time around, right? We end up with 0.707 equals 0.5 to the n power, where we have to now take the log of both sides, and then we can solve for n to be 0.502, and that gives us a chlorine order of 1/2. We did say that you could have halves, you could have negative numbers, so this is a fractional rate order, and that's unusual, but it does happen, and we certainly should be able to solve for it and handle it if it did occur. So now that we've inspected both reactants, we can say that the rate of this reaction equals the rate constant K times the concentration of CH3Cl to the first power, Cl2 to the 1/2 power. That gives us an overall rate of reaction of 1.5, right? The 1 plus the 1/2. So to find the units of K, remember overall K needs to, or rate needs to equal molar per second. So therefore K in this example has to be molar to the -1/2 seconds to the -1. So it's unusual. We wouldn't expect to see a lot like this, but it does happen, and there's an example of that happening. If we want to find the actual numerical value of K, we could plug in any of those 4 reaction conditions, because we know what the rate is. For example, here we look at run number 4. The rate was 0.115 molar per second. That's going to equal K, which is our unknown, times the concentration of the CH3Cl, which in this case for run 4 was 0.200 molar. The concentration of Cl2 was also 0.200 molar in that example, but that one we need to raise to the 1/2 power. When we do all the math correctly, we end up with an overall value of K of 1.29, and again the units molar to the -1/2 seconds to the -1. All right, so we've covered a lot of ground. Our last topic for today will be the integrated rate laws. So for the reaction A goes to product, the rate law depends on the concentration of A. We've said that, again, assuming that we're anything but zero order, we would have some dependence on the concentration of A. An integrated rate law is a rate law, but it's from a calculus point of view, Calc 2 for those who know the term integration, right? It shows the relationship between the concentration of A and the time of the reaction, and so it suggests a way to tell a reaction's order based on experimental data in a different way than what we've done so far. So students tend to like the integrated rate laws for that reason, and I think you'll see why in just a moment. So just after I tell you how great they are, the drawback of the integrated rate laws is typically you have to know which one to apply, right? There's 0, 1st, and 2nd order integrated rate laws that we'll look at here in our course. So the way you can tell which rate law applies is to look at the graphical representations, right? So if you have the plots, plot of concentration of A versus time, ln concentration of A versus time, and 1/, concentration of A versus time, that would tell us whether we're dealing with a 0, 1st, or 2nd order reactant, right? Whichever plot gives you the straight line determines the rate order with respect to A. So if the plain old concentration versus time gives you a linear plot, then you're 0 order with respect to A. If the natural log of concentration versus time gives you the straight line plot, then you are 1st order with respect to A. Finally, if 1/, concentration versus time gives you the straight line plot, then you're 2nd order with respect to A. So we talked about that a little earlier, just reminding you of that feature because that's going to help you to apply the correct integrated rate law. Okay, so let's deal with 0 order reactants first. So here the rate would equal K times A to the 0, or just rate equals K for a 0 order reaction with only one reactant. The integrated rate law for a 0 order reaction is concentration of A sub T equals minus KT plus concentration of A sub 0. So what that means is the concentration of A at a given time, whatever time we select, equals the minus KT plus the concentration of A initially at the very beginning. The graph of A versus time is a straight line with slope minus K, and y-intercept is the A sub 0, the concentration initially. Rate is going to equal molar per second, and so therefore the units of K are also molar per second, right, because rate equals K in this example. And the half-life relationship, a topic that we're going to get to next time is T1/2 equals initial concentration of A divided by 2 times that rate constant. If, on the other hand, we think about a first order reactant, now rate is going to be K times the concentration of A to the 1 power, or rate equals K times A concentration for first order reaction with only one reactant. Integrated rate law here is going to be the natural log of A equals minus KT plus ln of A sub 0, or we can rearrange that if you know your rules of logs and natural logs. Ln of A sub t over A sub 0 equals minus KT is another way to represent that idea. This time around, it's a graph of natural log of A versus time that gives a straight line, and the slope in this case is minus K, and the y-intercept is the ln of A sub 0. Our rate has units of molar per second, so the units for K here are just per second because you're going to get the rate, molar units from the concentration of A. And the half-life relationship for first order kinetics, T1/2 equals 0.693 over K. Notice there's no concentration term here for the half-life of a first order reaction. It's constant. Finally, for a second order reactant, rate equals K times A to the second power for second order reaction. The integrated rate law for second order kinetics is 1 over A sub t equals KT plus 1 over A sub 0. Here again, a graph of 1 over A concentration versus time gives a straight line with slope equal to K and y-intercept equal to 1 over A sub 0. Since rate, of course, always equals molar per second in our course, the units of K for a second order reactant would be molar to the -1, seconds to the -1. And the half-life relationship here, T1/2 equals 1 over K times A sub 0. All right, so there we have it. All right, and so here it is, our summary table for rate laws. So we talked about examples where orders can be a half. We saw that with the chlorine in that one problem that we worked. Orders can be negative, but by and large, we tend to focus in this course on 0, first, and second order. So you can see for 0 order, our rate law, rate equals K times A to the 0 power, or rate equals K in that example. Units of K would be molar per second. And our integrated rate law is given. Our plot that we're looking for is concentration versus time to yield a straight line slope, which would be equal to minus K with a y-intercept of A sub 0. And then a half-life expression of T1/2 equals A sub 0 over 2K. For first order kinetics, we have rate equals K times A to the first power. So units of K would be just plain old seconds to the -1. And then we have a couple different forms of that first order integrated rate law. To show it graphically, we're looking at a plot of ln of A versus time to give a straight line with slope minus K and intercept of ln of A sub 0, a T1/2 expression of 0.693 over K. Finally, for second order kinetics, we have a rate equal K times A to the second power. Units of K will be molar to the -1, seconds to the -1. Integrated rate law 1 over A sub t equals KT plus 1 over A sub 0. It's going to be a plot of 1 over A times versus time to give us a straight line with slope K and y-intercept equal to 1 over A sub 0. And finally, our half-life expression for second order would be 1 over K times A sub 0. So lots of ground covered today, still lots more to do in kinetics. Hopefully you're excited rather than overwhelmed by this introduction to the topic.